Hello everybody, getting ready to do lesson 7.3 part 3 of pre-calculus math today, our classwork. And today's classwork will start out, you have a huge notebook assignment here of 36 points in your notebook, 7.3 part 3, and you only got 20 points here at classwork. So it's mostly taking notes today, students. Be prepared for that. And we go right into your notebook here. Graphical interpretation of three variable systems. Solutions of equations in three variables can be represented graphically using a three-dimensional coordinate system. To construct such a system, begin with XY coordinate plane in a horizontal position. So here's our Y, here is our X. Then draw the z-axis, here's your z-axis here as a vertical line through the origin. Every order triple xyz corresponds to a point on the three-dimensional coordinate system. For instance, the points corresponding to -2, 5, and 4, -2, 5, and 4 be over here, and then 2, -5, and 3, 2, -5, and 3 be over here. And 3, 3, and -2 would be down here. 3, 3, -2 would be actually down here. The graph of an equation in three variables consists of all points x, y, and z that are solutions of the equation. The graph of a linear equation in three variables is a plane. Sketching graphs in a three-dimensional coordinate system is difficult because the sketch itself is only two-dimensional. One technique for sketching a plane is to find the 3 points at which the plane intersects the axes. For instance, the plane 3x plus 2y plus 4z equals 12 intersects the x-axis at 4, 0, 0, the y-axis at 0, 6, 0, and the z-axis at the point 0, 0, 3. By plotting these 3 points, connecting them with line segments, and shading the resulting triangular region, you can sketch a portion of the graph as shown. So this is what that graph would look like for this expression here, 3x plus 2y plus 4z equals 12. This would be a graphical representation of that. The graph of a system of three linear equations and three variables consists of three planes. When these planes intersect in a single point, the system has exactly one solution. So this will be an example of that, where three planes intersect at one point. You got 1, 2, and then 3 here. When the three planes have no point in common, this system has no solution. This system here would be no solution. This system here would be no solution. There's no single point of intersection. When the three planes intersect in a line or a plane, the system has infinitely many solutions. So solution one line here, solution one plane here. So this system has infinitely many solutions for these three planes. Partial fraction decomposition. So a rational expression can often be written as the sum of two or more simpler rational expressions. For example, this rational expression here, x plus 7 over x squared minus x minus 6, can be written as the sum of two fractions with linear denominators. That is, x plus 7 over x squared minus x minus 6 can be written as 2 over x minus 3 plus -1 over x plus 2, and we've derived these partial fractions by factoring this quadratic into two binomials. Each fraction on the right side of the equation is a partial fraction, and together they make up the partial fraction decomposition of the left side. So this is an equal expression of that. Decomposition of n of x over d of x into partial fractions. Divide if improper. Divide if improper if n of x over d of x is an improper fraction, meaning the degree of n of x is greater than or equal to the degree of d of x, and that would make it an improper fraction. Again, where the degree of n of x is greater than or equal to the degree of d of x, then divide the denominator into the numerator to obtain n of x over d of x equals polynomial plus n of 1x over d of x. So that would be our next step there to make it a proper fraction. And apply steps 2 and 3 and 4 below to the proper rational expression n of 1 of x over d of x. So this is what we would do here. We'd end up with a polynomial plus this, almost as like a remainder of our division. To do that, factor our denominator. Completely factor the denominator into factors of the form p of x plus q quantity to the m power and ax squared plus bx plus c to the nth power, where ax squared plus bx plus c is irreducible over the real. So if it's irreducible over real numbers, then linear factors for each factor of the form px plus q to the m power. The partial fraction decomposition must include the following sum of m fractions. So we have a1 over px plus q plus a2 over px plus q squared plus a to the m over px plus q to the m power. So quadratic factors for each factor of the form ax squared plus bx plus c to the n. The partial fraction decomposition must include the following sum of n fractions. So we have b1x plus c1 over ax squared plus bx plus c plus b2x plus c2 over ax squared plus bx plus c to the second power, on and on here to b to the n x plus c to the n over ax squared plus bx plus c to the n. So let's try one now. Let's put this into practice. Partial fraction decomposition, distinct linear factors. Write the partial fraction decomposition of x plus 7 over x squared minus x minus 6. The expression is proper, so we have a proper situation here because our degree of our numerator is less than the degree of the denominator. So factor the denominator. So we're going to break this down. Because x squared minus x minus 6 equals x minus 3 multiplied by x plus 2, you should include one partial fraction with a constant numerator for each linear factor of the denominator and write x plus 7 over x squared minus x minus 6 equals a over x minus 3 plus b over x plus 2. So we need a constant here for a and b. How do we get that? Multiplying each side of this equation by the least common denominator, x minus 3, x plus 2, leads us to the basic equation here of x plus 7 equals a times x plus 2 plus b times x minus 3. There's our basic equation. And then our distributive property here, when you distribute that through, we have ax plus 2a plus bx minus 3b. And we end up with a plus b times x plus 2a minus 3b, right in polynomial form. Well, we have that. Because two polynomials are equal if and only if the coefficients of like terms are equal, you can equate the coefficients of like terms to opposite sides of the equation. So x here would be, here's our coefficient here, a plus b, and then for our constant here, 7, we would have 2a minus 3b here for our constant. Equate coefficients of like terms. You can now write the following system of linear equations. A plus b equals 1, a system, or rather equation 1 here. And then 2a minus 3b equals 7. That will be our equation 2. So now we have a system here. We broke that down, that quadratic, into a system of equations is what we've done. So having done that, you can solve the system of linear equations as follows. So here's our system here. A plus b equals 1, 2a minus 3b equals 7. This becomes, multiply equation 1 by 3, so we're going to multiply that by 3a plus 3b equals 3, and then write equation 2. So now we have 2a minus 3b equals 7. So now we're going to add our equations, and we end up with this. 5a equals 10. We got rid of our b. From this equation, you can see that a equals 2. Okay, good. We found out what a equals, finally. By back substituting this value of a into equation 1, you can solve for b as follows. So a plus b equals 1, and then 2 plus b equals 1, b equals negative 1. So now we have a value for b. So the partial fraction decomposition is x plus 7 over x squared minus x minus 6 equals 2 over x minus 3 minus, because of our negative 1 here, minus 1 over x plus 2. So here's our a, here's our b over our decomposed fraction. Check this result by combining the two partial fractions on the right side of the equation, or by using a graphing calculator. By using a graphing calculator, these should be the same on your same viewing window. Okay, let's try one now. So, write the partial fraction decomposition for the rational expression. Here's our rational expression. Check your result algebraically by combining fractions, and check your result graphically by using a graphing calculator to graph the rational expression and the partial fractions in the same viewing window. So 5x, and then when we factor this down, we have 2x minus 1, x plus 1, and we know we're going to have an a plus b here. So when we have our a plus b here, here's our decomposed denominator here. So now we can solve for a. 5 minus x will equal a times x plus 1 plus b times 2x minus 1. So we're going basically we're like cross multiplying here, and we get a plus 2b. 5 minus x would be equal a plus 2b x plus a minus b here for that. And then when we continue on our problem here to solve this, we have a plus 2b equals negative 1, and this means a equals negative 1 minus 2b, and then a minus b equals 5 in that situation there. And then once we know that, we have negative 1 minus 2b, quantity minus b will equal 5, therefore b will equal negative 2 in this situation. CB will equal negative 2, and a will equal 3 from this situation here. Knowing that, again, here's our decomposed denominator here. We have a is 3, b is negative 2, so 5 minus x will equal 3 over 2x minus 1, and then negative 2 over x plus 1. And that is our 7.3 Part 3 classwork for pre-calculus math. Here's my email if you need solution PowerPoints, class worksheets, note-taking guides, any other course materials. Thank you very much.